Picture this. You've got a multi-billion-dollar rocket sitting on a launch pad built by thousands of engineers and has the world's most advanced computer systems. But none of that matters if you miss the clock. You have only one chance to leave Earth, and if you're off by even the fraction of a millisecond, you're not going to make it to space. This is the incredible high-stakes engineering of the launch window. Hi everybody, welcome back to the Space Blast, and my name is Sathik Ranjanagi, and I'll be your host for today's video. With that, let's figure out why rocket science shouldn't be missed. So, what exactly is a launch window? This is not just a suggestion. A launch window is a specific mathematically designed time frame when a rocket must lift off the ground. And if you miss it, you're just an expensive lawn ornament on a launch pad. Why is it so critical? It all comes down to the alignment. When you want to rendezvous with a spacecraft like the International Space Station or with another planet, your paths have to cross in the future. Because the Earth is spinning, your launch site has to line up perfectly with the target's orbital plane. And if you miss it, the changes required to correct this error might be mathematically or physically impossible. This is all about fuel efficiency. You want to get your rocket up into space using the bare minimum energy. Now, not all windows are the same. Each window is classified by its flexibility. First, we've got the instantaneous window. This is the no room for error option. This window lasts for maybe a split second to a couple of seconds. It's used on missions like going to the ISS, where the rocket has to be perfectly aligned with the target. And then we've got the extended window, the engineer's best friend. This gives ground controllers a bit of leeway as they can have time to refuel the rocket, and they also have time to correct the rocket's path for minor delays. This window can last for around a couple of minutes to a couple of hours. And windows are also classified by their destination. You've got daily orbital windows, which are used for things orbiting Earth. And then you've got interplanetary windows, which are used for deep space missions and are governed by the planet's alignment themselves. The frequency of these windows depends entirely on the mission. For example, if you were launching a mission to low Earth orbit, you would have continuous or multiple daily windows. But the further you go out, the rarer the party becomes. Mars is the ultimate example. Because Earth spins faster around the Sun compared to Mars, they line up only once every 26 months. Yes, every 26 months, which is 2 years. So, if you were to launch a mission like Mars Express, you would have had the window for 4 weeks. And if you were to launch a mission to Mars in 2020, that window was open from July to mid-August. So, when's the next window? November to December of this year. And what about the next one? December of 2028 to January of 2029. So, if you want to go to Mars, please make sure to mark your calendars because the date's approaching pretty fast. But if you're watching this video, chances are you're likely not going to make it to Mars. So, let's just say you accidentally missed the launch window. What do we do now? Well, it depends entirely on how far you're trying to make it into space. If you're going to low Earth orbit to the International Space Station, chances are you can try again after 24 hours. Yes, you're late, and while it's annoying, it's not that big of a deal. But missing a mission to Mars, however, that's a shelve the mission for 2 years type of failure. And don't try and launch outside the window. You're going to get nowhere. Because of all the fuel it takes, it's going to be physically unrealistic to send that satellite outside of the window. And don't forget how much these space agencies have to pay to store these satellites for the next window, if they even do that. And don't think test flights are exempt from this. No, no, no. They also have launch windows, even though they don't have any payload, just because they need proper lighting, visibility, tracking, and telemetry coverage. It's not about where you're going, it's about what the mission needs to validate its goals. So, you may say, if you're so good, how do you calculate it all? What's the secret? There is no secret. Scientists just do a lot of orbital planning before the mission. They account for things like how much fuel is going to be needed, how far are we going, what's the mission going to be about, and are there any gravity assists, you name it. And they also have to account for Earth's rotation to avoid costly corrections in space. They do this all on a plot called a pork chop plot. This plot helps them understand how much energy is going to be needed to send the payload into space against the launch time. Not only that, they have to be precise. They can't be a millisecond too early or a millisecond too late. And not only that, but they have to comply with FAA guidelines and with range safety. There's a whole lot of rules and a whole lot of planning required to send a rocket into space. So while SpaceX may be sending rockets like fireworks each day, it's not easy. You have to be precise. You can't be a millisecond off. And one wrong move can end the entire mission in a blink of an eye. So, do launch windows repeat? Yes, but once again, it depends on where you're heading to. Missions in low Earth orbit can repeat about every 24 hours. Missions to the moon repeat about every 27 to 28 days. And missions to Mars repeat about every 26 months. No matter how beautiful, how advanced, how precise your rocket may be, nature loves to interrupt. You see, you may be counting down to the final 10 seconds. You may say 0, but nature can throw you rain, thunderstorms, wind shear, space weather, solar storms, basically anything that can stop a rocket launch. In those situations, you're going to probably hear a no-go. The meteorology has to be perfect across all aspects, the launch site and the abort zones in case there are humans flying on board. It's just too big of a risk to leave out. So there you have it. That's the launch window. It's a bit like a game of celestial darts, where the dartboard is millions of miles away and you are expected to hit the bullseye. It's an ultimate test of patience and physics. I'd say trying to launch a rocket is a bit like a first date. If the timing isn't right, it's probably not going to work out. Thank you so much for joining the Space Blast, and if you support more content like this, please make sure to hit the like and subscribe button and smash that notification bell to receive daily updates on future content that I post. Thank you so much for joining the Space Blast once again. You rock! Until then, see you next time.
T-minus 10, 9, 8, 7, 6, 5, 4, 3. We have ignition. And liftoff of the first United Launch Alliance Vulcan rocket, launching a new era in spaceflight to the moon and beyond.
Two good SRBs, hitting peak pressure on the SRBs. Everything looking good. Programs in, coming into normal rates for that event. We have good hydraulic pressure on both engines, good chamber pressure on both engines, everything looking good. Coming up on 60 seconds into the flight, everything looking good. Two good engines, two good SRBs. Body rates look good, nice and slow. And we did our first throttle point in the BE4s, everything looking good. And passed through Mach 1, we're now supersonic coming up on the next key. We're at max dynamic pressure, everything looking good, we're rolling off on the SRBs. cutoff on the SRBs. Coming up on jettison. After 30 seconds. 15 seconds. Jets, continue to operate nominally. Seeing expected PU activity on the boost remains. And we have separation of both SRBs. Everything looking good. BE4s continue to operate normally. Coming up on 2 minutes into the mission. We are now 17 miles an hour.
We just heard confirmation of solid rocket